Project 2.1 Digital to Analog Conversion. The purpose of this project is to explore how the R2R resistor ladder converts digital signals into analog voltages. New hardware concepts, including Thevenin's equivalent circuits and superposition theory, are used to explain how this circuit is able to translate stepped binary inputs into smooth analog outputs. This project also serves as an introduction to PCB design in Easy EDA and 3D printed PCB encasement designs in Fusion 360. Here's how the R2R DAC works. Each switch on the DIP rocker represents a binary value of 0 or 1. The leftmost switch, bit 7, is the most significant bit, and the rightmost switch, bit 0, is the least significant bit. Each bit corresponds to a fraction of the maximum voltage, which is 9 volts, increasing from right to left. When a switch is flipped high and connected to 9 volts, its corresponding voltage fraction is added to the total output. This chart shows how much voltage each digital switch contributes to the voltage output. The most significant bit, bit 7, contributes 1/2 of the total voltage, or about 4.5 volts. Bit 6 contributes 1/4 of the total voltage, or about 2.25 volts. Bit 5 contributes 1/8. Bit 4 contributes 1/16. Bit 3 contributes 1/32. Bit 2 contributes 1/64. Bit 1 contributes 1/128th, and bit 0 contributes 1/256, which is too small to show up on this display. So what does this mean? The output voltage increases in equal steps as the binary number increases. Setting all switches low produces 0 volts, and setting all switches high produces 9 volts. That means intermediate switch combinations produce proportionately scaled voltages, meaning the R2R DAC can convert its digital inputs into a smooth, continuous analog signal, like shown in the graph on screen. Thevenin's theorem is a technique used to simplify complex circuits into a single voltage source and a single resistor. Using Thevenin's theorem, the R2R DAC can be simplified to one equivalent resistance. Here's the complete schematic for the R2R DAC. We are going to focus on this part of the ladder though. R15 and R16 are connected in parallel, with R16 leading to ground. Because they are in parallel, their equivalent resistance equals 1 over 10.2 kiloohms plus 1 over 10.2 kiloohms to the power of -1, which equals 5.1 kiloohms, or simply R. So the circuit can be simplified into this new image. Look again though, this 5.1 kiloohm resistor is in series with another 5.1 kiloohm resistor, meaning their equivalent resistance equals 5.1 kiloohms plus 5.1 kiloohms, which equals 10.2 kiloohms, or 2R. This 2R is now in parallel with bit 1's 2R, and this cycle repeats. Eventually, at bit 7, you'll be left with two 10.2 kiloohm resistors in parallel, which simplify into one 5.1 kiloohm resistor. Therefore, the equivalent resistance of the circuit equals 5.1 kiloohms. Superposition theorem allows for the analysis of a circuit with multiple voltage sources by considering the effect of each source independently. Using superposition theorem, the R2R DAC's output voltage can be simplified into a simple equation. At bit 0, there are two 10.2 kiloohm resistors in parallel. Half the voltage of bit 0 is taken up by the first resistor. This means the circuit has half of bit 0's voltage at the junction between those two resistors. Since we established earlier the two parallel 10.2 kiloohm resistors simplify into one 5.1 kiloohm resistor, and the 5.1 kiloohm resistor is in series with the next 5.1 kiloohm resistor, this creates another 10.2 kiloohm resistors. The process of half of the voltage being taken up repeats because there are now two 10.2 kiloohm resistors in parallel. So at this junction, there is 1/4 of bit 0's voltage, and so on. After all 8 junction points, bit 0's voltage contribution is only 1 over 256 of its digital input voltage. Applying this to bits 1 to 7 as well, and adding each bit's output voltage, the total output voltage for the 8-bit R2R DAC powered by 9 volts is given by the equation on screen. This formula can also be extended to apply to an n-bit DAC with any input voltage to give this formula on screen. Thank you for watching.